Cyclotrons and synchrotrons. Beams of high energy particles such as high energy electrons and protons have been enormously useful in probing atoms and nuclei to reveal the fundamental structure of matter. Such beams were instrumental in the discovery that atomic nuclei consist of protons and neutrons, and in the discovery that protons and neutrons consist of quarks and gluons. The challenge of such beam is how to make and control them. Because electrons and protons are charged, they can be accelerated to the secured high energy if they move through large potential difference. Because electrons have low mass, accelerating them in this way can be done in a reasonable distance. However, because protons and other charged particles have greater mass, the distance required for the acceleration is too long. A clever solution to this problem is first to let protons and other massive particles moving through a Morse potential difference so that they gain a modest amount of energy, and then use a magnetic field to cause them to circle back and move through a modest potential difference again. If this procedure is repeated thousands of times, the particle end up with a very large energy. Here we discuss two accelerators that employ a magnetic field to repeatedly bring particles back to an accelerating region where they gain more and more energy until they finally emerge as a high energy them. The cyclotron. Figure 28.13 is a top view of the region of cyclotron in which particles circulate. The two hollow D-shaped objects, each open on its straight edge, are made of sheet copper. These Ds, as they are called, are part of an electrical oscillator that alternates the electric potential difference across the gap between the Ds. The electrical signs of the Ds are alternate so that the electric fields in the gap alternate in direction, first towards one D and then towards the other D, back and forth. The Ds are immersed in a large magnetic field direction out of the plane of the page. The magnitude B of this field is set via a control on the electromagnet producing the field. Suppose that a proton injected by source S at the center of the cyclotron initially moves toward a negatively charged D. It will accelerate toward this D and enter it. Once inside, it is shielded from electric fields by the copper walls of the D. That is, the electric field does not enter the D. The magnetic field, however, is not screened by the copper D, so that protons move in a circular path whose radius, which depends on its speed, is given by equation R is equal to mv over qb. Let us assume that the instant the proton emerges into the center gap from the first D, the potential difference between the D is reversed. Thus, the proton again faces a negatively charged D and is again accelerated. This process continues, the circulating proton always being in step with the oscillation of the D potential until the proton has spiraled out due to the age of the D system. This resonance condition says that if the energy of the circulating proton is to increase, energy must be fed to it at a frequency that is equal to the natural frequency f at which the proton circulates in the magnetic field.